Here is a simple risk register built with ModelRisk to estimate the total financial exposure from the portfolio of risks that are listed and to determine which of the risks are contributing the greatest to the overall exposure. So the risk information is organized in columns. The first column, we have the risk ID, R001 for the first risk, R022 for the last one. A description that you can apply, which have no effect on the calculations. The third column, repeatable, asks whether or not the risk is repeatable. So some risks, for example, strike or a fraud or a fine, a system shutdown, these are all repeatable events, meaning that if it happens once, it can occur again. And some other risks, for example, loss of a license or the withdrawal for the product, they can only happen once. So this allows you to say that the risk is repeatable or not. So many of these risks here are yes, they're repeatable. Some of them are not repeatable. And then the next column asks, well, if it's a repeatable risk, what is the expected annual frequency? Meaning, on average, how many times would the risk event occur? If it's not repeatable, then what's the probability of that risk event occurring? This would always have to be within a particular time frame. So if the expected frequency would be over a year and the probability of it occurring would be within the year. Then we have data on what the financial impact might be for a single event should it occur. So if this risk, the first R001 occurs, the minimum loss that will be incurred will be $0.1 million, most likely 0.2, and the 90th percentile, the P90, of 0.6. We use P90 instead of the maximum because it's much easier to ask people about a realistic maximum rather than the absolute maximum value. Then to the right of that, we have the interpretation of this information. So we have a 3-point estimate, which is the interpretation of the minimum, most likely, and the P90. And this is a ModelRisk function. You can see, if I click F2, it says Vose 3-point estimate. So it's a 3-point estimate distribution and object. The object is a type of function or a class of functions that allow you to specify a distribution, but not actually simulate from it. You're simply determining which type of distribution you want to use. So for example, you could say, I want to use a normal distribution when the mean of 2, standard deviation of 3. That would be specifying the name of the distribution without actually running any calculations on it. If I click on that 3-point estimate, because it's a ModelRisk function, so it has the word Vose in front of it, I can click on the ModelRisk ribbon and I can click on View Function. And you will see it will pull up a graph of that probability distribution. And that's the same for any of the functions within ModelRisk. Having determined what that distribution is for the loss of an individual impact, then I can also determine mean. So in here, you can see this function says Vose mean. Vose mean of this 3-point estimate distribution is returning me the mean of that distribution directly in the spreadsheet. And you can see over here, I've created a graph, it's a scatter plot chart between the annual frequency or expected frequency and the mean loss of an individual event. And if you plot those in a chart or use log scales for both axes, then a straight line running through this chart gives you values of the same expected value or average loss. So because people like using color schemes a lot for ranking risk, you can see here the red, that line, any risks falling on that line had the largest impact equally. Any risk falling on the orange line has a medium high impact, medium low impact, the yellow, and everything green will have a very low impact. In next column, we're simulating the number of events that will actually occur using the formula. If the repeatable is yes, then we're going to use a Poisson distribution. This is the standard distribution for modeling frequency of events that concur multiple times. If not, it's a Bernoulli distribution. So you can see here that we've got 0, 0, 0, and then 4. So this is a repeatable. Risk number 4 is repeatable. On average, it could be 4 events. If I click on that and click on the view function, then you can see I've got a Poisson distribution. That's the one that's being used, or the Bernoulli. The input value for the Bernoulli would be wrong because it's 2.5. So this is the Poisson distribution that's being used. If I click, you can see it has some probability of 0 events, 1, 2, 3, 4. That's what's being sampled right now. If a probability or frequency is very small, then you would see that they actually look very much alike. So here we have a 0.02 frequency or probability, and it wouldn't much matter which one we use. So if I show you what the Poisson distribution looks like here, you can see a high probability of 0 and a probability 1. There is some probability of it being greater than 1, but it's extremely insignificant. If I compare that with the Bernoulli distribution, they're essentially the same, I think you can see. When I hit the F9 key, these numbers change. So we're simulating a different number of events for each type of risk that could occur. And in the final column, we're calculating the aggregate loss. So here's where we pull all this information together. So nominated this as an input. We've given it the name risk number 1, and it's got the units of millions of dollars. And it's Vose aggregate MC. There are several aggregation functions within ModelRisk. The MC is Monte Carlo, and it's taking 2 parameters. One is the number of events that we're having to add together. So in this case, 0 right now. So it's 0 events. It's going to total up to 0. And then here, how many probability distributions we're needing to sum. So in this cell, we've got 2 events have occurred, each of which is somewhere between 2.9 and $14 million in loss. One might be high, one might be low. And so this aggregate MC function is simulating 2 separate events and summing them together. If I click on the aggregate MC link here, you can see there are the 2 events. This is the individual loss distribution. And this is a little simulation to give you an idea of what the aggregate looks like. So for 2 events where roughly speaking, it's about 9 on average for any individual event, we expect that the total will be somewhere centered around 18. Then I've just got the total at the bottom, which is a sum and named as an output, given the name total loss in millions of dollars. All I need to do is run the simulation. 2,000 samples is going to be enough. Start the simulation. Do I want to save the old results? No, thank you. Simulation runs. You can see in the simulation progress interface, when it's finished, the results viewer pops up, which will show you any pre-prepared graphs that you may have created in the previous runs of the model, and you can still create more graphs. You can see a more thorough review of the results viewer application in a separate video. You can look in the link for a list. So what we have here, we have a Pareto distribution for the total loss amount, total loss, and this is a cell, this is a unit, and you can see this cumulative curve together with the histogram curve showing you the mean, the statistics on the right, etc. So there's a 95% chance that the total loss will be less than $123 million. There's a tornado chart. The tornado chart shows us which of the risks are contributing the greatest to the average expected loss. So you can see here the risk number 4, if it was not to occur, it would be the average expected loss would be somewhere around $56 million. But if it occurs with the highest frequency at somewhere near the highest values, it would be up to $108 million. And so the longer the bar, the more the effect that this has on the mean of the total loss. We also can look at, say, financial capacity. For example, if we have $120 million in reserves to cover any potential risks, we can look at the probability that would be sufficient. So here it says there's about 93% chance that we will have sufficient reserves. He colored this por carrier of risks.